If I give you a number with thousands of digits, could you tell if that number is prime or not? Well, this usually can take up to millennia. Say, for example, you want to test if any number p is prime. 43? Good choice. Now, we can divide 43 by all the natural numbers less than it, and see if they result in an integer. For example, dividing 43 by 2 does not equal an integer. So is 3, and 4, and 5, and 6. And if we go on to 43 minus 1, which is 42, we can come to the conclusion that 43 is a prime number. So how do computers detect if numbers are prime or not, and why aren't they 100% sure that it is? Well, it all starts in the year 1640, as French mathematician Pierre de Fermat found something interesting about prime numbers. He found that if p is prime, then a, which is less than p, to the power of p minus 1, mod p, which takes the remainder of the division by p, is always equal to 1. And we can rewrite this as a to the p minus 1 is congruent to 1 mod p. Fermat later described this as Fermat's little theorem, which states if p is prime, a to the p minus 1 is congruent to 1 mod p, where a is less than p. Let's test if 43 is prime, and we'll say a equals 2. Firstly, we do 2 to the power of n minus 1, which is 42 in this case, and then take mod 43. In this case, a is congruent to 1, so that means 43 is prime. And that is correct, 43 is prime. But does Fermat's little theorem always work? Well, to test this, let's try and detect if 561 is prime, and we'll use a as 100. So we do 100 to the power of 560 mod 561. And if you're interested on how I calculate that bit, I put the code on the screen right here. This is in Python. And with all that stuff out of the way, 100 to the power of 560 mod 561 is equal to 1. So that means 561 is prime. But 561 is not prime, it's composite. Because we know that 3 times 187 is equal to that. So let's try a equals 77. For example, we take 77 to the power of 560 mod 561, which equals 154, which means 561 is composite. So, what goes in the base? How do we know what a is to not falsely declare prime or composite? If you look at all the bases for 561, the ones in red do not work and falsely declare 561 as prime, and the green ones work, declaring 561 as composite. Now, 561 is a part of a special sequence called the Carmichael numbers. It goes 561, 1105, 1729, and so on. Numbers in the Carmichael numbers, when put together as p, failing Fermat's little theorem. In the year 1994, mathematicians William R. Alford, alongside Andrew Granville and Charles Pomerantz, proved that there were infinitely many Carmichael numbers. This showed the great flaw in Fermat's primality test. 2 decades earlier, in the early 1970s, PhD Gary Miller was already working on a primality test that avoided the disturbance of Carmichael numbers. Let's test if 561 is prime using the test, and let's fit a is 100. What Gary Miller does is he first takes 100 to the power of 560 and takes mod 561, just like in Fermat's test. In this case, it's congruent to 1 mod 561. This is the stage that Fermat's primality test falsely declares 561 as prime. What Miller does now is divides that 560 by 2, giving us 280, and then takes 100 to the power of 280 mod 561, which is congruent to 1. He does that multiple times until the exponent is not divisible by 2. Each time, this now reveals a sequence. As you can see, you can put this together in a sequence as so. Now, for 561 being prime, Miller applies 2 rules. Number 1, the first number is a 1, which checks out. The second rule is any number after 1 is either 1 or p minus 1. Since the first digit is a 1, we check this digit over here, which is 1 or p minus 1. Since that digit is 1, we check 67, which is not 1 or p minus 1, so it fails the second rule. So that means 561 is composite. But Miller's primality test still had an issue. To test this, let's test p equals 221 with an a value of 174. Putting these together, you make the following sequence, which goes 1, 220, and 47. We can now apply the rules. For 221's prime, number 1, the first number is a 1, which in this case satisfies the first rule. Number 2, any number after a 1 is either 1 or p minus 1. Hence the first digit is 1, we need to test 220, which is either 1 or p minus 1. So it satisfies both of the rules. So that means 221 is prime. But 221 is not prime, it actually factors into 13 times 17. So does this mean that Miller's test was in its grave? Well, not entirely. Miller found out that for all possible values of a, more than 50% of them would work. So, for just 10 iterations, the chance of an incorrect answer is about 1 in 1,000. For just 100 iterations, you have a better chance of winning the lottery. Later, he met with Miller-Rabin, a professor at Harvard. He told him that for all possible values of a, more than 75% of them would work. Implementing this iteration thing into code, we can just set up a basic for loop for in range of 10, which is our iteration count. Then we can call our function, which is primality, and then we can put the result in an array. After this, we can output our array, and it might look something like this. I've marked p prime, composite being c. Now, all we need to do is look at that 10th item. The chance of that 10th item being incorrect is about 1 in a million. But it still begs one more question. After Miller-Rabin revolutionized the Miller test, they eventually called it the Miller-Rabin test. But other tests do exist, such as the AKS test, which basically says if p is prime, then all the coefficients of x plus 1 to the power of p minus x to the power of p minus 1 are all divisible by p. But the downside of this is raising x plus 1 to the power of a number with thousands of digits could take more space and time than we have in our observable universe. This video is about how computers generate primes, not how to detect if things are prime. Well, so how do we actually generate huge primes? Well, all we have to do is just start with a while true loop, and then we can check our primality of a random value from 1 to 10 to the power of how many digits we want it to be. Then, if our result is composite, then we restart the loop, generating a different value each time. Else, if the result is prime, then we just print the result. And it might seem that this is a very slow method to do it, but on average, for a number with thousands of digits, this only takes about 1,000 tries, which computers only take milliseconds to do. Well, that's all for today. If you like the style of content I post, please consider subscribing. And that's all for today. See you next time. Bye!